So what is software-defined networking? So if you look at a traditional network, you have vertical integration. So everything is built into the device, all the firmware and hardware and software control plane and drivers and APIs, and it's all vendor specific. So you have proprietary protocols and interfaces and APIs and CLIs, and you have these specialized appliances, and then configuration becomes complex and decentralized because every time you need to make a network-wide change, you basically need to configure each device individually through their CLIs. Now, in software-defined networking, the main principle behind it is the decoupled control and data planes. What that means is the data plane, which is where traffic forwarding happens, that remains in the devices, and it's the only thing they do. They forward traffic. The control plane, or the decision making or the logic behind how to forward traffic, that is taken off of the devices and into a single centralized piece of software that we call the controller. And that is basically running on a computer somewhere. Now we have with the controller then a centralized view of the network. The controller has the visibility into the entire topology, and the controller can run, because it's software, it can run any sort of traffic engineering algorithm application. And because the devices become simpler in the sense that they only have to forward traffic and do nothing else, then we can have a state of vendor agnosticity, because it doesn't matter who we buy hardware from, as long as the interface between the controller and the devices is well defined and well implemented. It helps to understand SDN if we look at the de facto southbound protocol. That is the protocol that the controller uses to communicate with the devices, and that is OpenFlow. So OpenFlow works like this. We have a set of match and action pair that defines an OpenFlow rule. So a match condition will match packets in the network against any set of fields in the IP stack. It could be layer 2 MAC addresses, it could be layer 3 IP addresses, it could be TCP or UDP ports. It could even go in higher layers or even lower layers with, for example, optical extensions for wavelength switching. But the point here is that OpenFlow has this layerless nature, meaning a switch that is OpenFlow enabled is not going to be called a layer 2 switch or a layer 3 router. We call them switches as a generic term, but it could really be a switching element that is matching on any layer of the network, and this could be done even at the same time. So a switch can at the same time be doing MAC learning and layer 2 switching, and on top of that it could also be using some layer 3 routing and even some layer 4 dropping to act as a firewall. So a switch can be anything with OpenFlow, and the actions are simply to forward the packet out on a specific port or to send that to the controller, so the controller decides what to do with it. An action could even be to modify some of the header fields before forwarding it, or it could be a drop action, in which case the packet won't be forwarded. And the last thing that the OpenFlow protocol defines are statistics, which are of course very important for monitoring and so forth. Now here's an example of how it would work on a real scenario. So we have a very simple topology with 3 switches, and host A wants to send traffic to host B. So that traffic is going to come in through port 1 on the first switch on the left. The switches are all, they don't have any OpenFlow rules on them yet, and they are working in this scenario here, what is called reactive forwarding. So when you're reactive forwarding, the switches are gonna ask the controller every time that it receives packet that it doesn't know what to do with. So in this case, we'll query the controller will send back after the controller performs its own traffic engineering calculations that you previously defined. The controller will send back the OpenFlow rule for that switch to be able to handle that kind of packet. So in this case here, it is matching the traffic coming from port 1 and dashing to MAC address B to be outputted on port 3. So that's what the switch is going to do. And then on the next switch, the same thing is going to happen. It's going to receive a traffic that it doesn't know what to do with. And it could be that on the first moment that the first switch asks the controller what to do, the controller would already install the flows all the way in all the switches affected for that kind of traffic, in which case this here wouldn't be happening. The switch number 2 on the right would know what to do. But let's assume that that's not the case. So the switch is going to ask the controller what to do. The controller is going to reply back with the OpenFlow rule for that as well. And the traffic is going to reach server B. Now another mode of operation in software-defined networking is proactive forwarding. In this case, the controller installs on the switches beforehand all the OpenFlow rules for all the traffic that is expected in that network, so that the switches don't have to ask the controller what to do when packets come in through their ports. This could still happen if there is some extraneous traffic that the controller hadn't predicted, but for the most part, the switches will know what to do with traffic. And finally, one thing to mention about SDN is the northbound layer, also referred to as the policy layer, and that's when you define on a high level or on a policy fashion what you want to do in the network. So in this example here, we want to allow traffic between clients or servers A and B on specific ports 22 and 443, and we define this in this high level fashion, and this will depend on the specific northbound and the API implementations in the controller. This could be a JSON formatted request, it could be a drag and drop menu in the GUI, or it could be anything else. This will be sent to the controller, and the controller will map that request to OpenFlow rules that would realize that policy. Now, one good way to see how SDN is really a good advantage is if you compare it to a spanning tree protocol running on your commodity network with simple layer 2 switching. With spanning tree protocol, if you have a loop in the network, spanning tree protocol is going to block some of the redundant links so that traffic is not looped in the network, and what ends up happening is that you lose extra bandwidth that you could have to forward your traffic, and it's not very efficient. But if you use SDN, if you have commodity switches that don't do layer 3 routing, you could use SDN or an SDN controller to run routing algorithms and to proactively install routing tables, which would be OpenFlow tables on the switches, and the switches would act like routers even though they don't actually are themselves routers, in the sense that they don't have any built-in intelligence to route traffic and to avoid loops in the network. but the SDN controller can do that for them. So even though we can have the same kind of cheap hardware, so to speak, because they are commodity layer 2 switches, we can have an intelligent network and more efficient network than we would otherwise. So to summarize the ideas behind software-defined networking, the main principle behind it is the decoupled control in data planes. So the control plane is a single centralized controller running on a computer, and the data plane are the devices themselves. SDN defines a virtually centralized controller. Controllers can be physically distributed for scalability purposes, but it is virtually centralized. It is vendor agnostic, and it defines an open standard interface. And finally, SDN enables programmability and virtualization of networks, which is to say, SDN makes them easier to implement than other traditional technologies. That's all, and thank you for watching. If you like to hear more of these kind of videos, please hit subscribe.